Hello everyone, welcome to the last video for AP Physics C Mechanics. This is about rotation and rotational motion. Our next video in this series is actually going to be on AP Physics C Electricity and Magnetism, which is always fun. But yeah, without further ado, let's get into the content of this video, which is rotation and rotational motion. As always, there's going to be like a content review first, and then we're going to have 8 problems to work through today. And I try to pick a nice mix of problems that'll give you a hang of what the content's about. So let's get started. What is rotational motion? So rotational motion is motion around an axis, so like a spinning object or something like that. For example, a car wheel while it's driving. The axis of rotation is just the fixed axis that the object rotates around. And we're going to be dealing mainly with rigid objects, which is an object that has a definite shape or size. For example, a car wheel. And one rule that you're going to need absolutely in this unit, and actually in electricity and magnetism too, but it's the right hand rule. And you might have heard of it from circular motion, or maybe like some other physics or math topic, but it's prevalent a lot in physics. But we're going to need it a lot in rotational motion and also in electricity and magnetism. So what is the right hand rule? Basically, it's a rule that determines the direction of angular quantities. If an object if the direction is counterclockwise, right? If it's, for example, spinning counterclockwise, then it's positive perpendicular to the circle. So let's say you have like this, right? It's a horizontal plane like this. Then it's going to be upwards, so positive, perpendicular to the circle. And how can you remember this? Well, that's where the right hand part of it comes in. You make the circle with the 4 fingers of your right hand, and whatever direction your thumb points in will be the direction of the quantity. Now I can't obviously show you that, but I can kind of draw a hand. So like if you have your 4 fingers pointing this way, your thumb will automatically point upwards, and so you know that your direction would be positive or upwards. That's a terrible hand, but you get the point. Same thing, if you have something moving clockwise, it's going to be downwards, because again, if you do your 4 fingers this way, your thumb is going to be pointing downwards naturally for your right hand. If you do your left hand, it's going to be the opposite way. So just do your right hand. So that's the right hand rule. All right, now let's move on to kinematics. So basically, rotational motion is like a review of everything we've done so far. Kinematics, forces, work, energy, power, momentum, things like that, but all like with a spinning body. So it's just, you're going to come across many familiar terms, but they're just going to be a bit different this time. First of all, you might know this from math, or you should know this from math. A radian is just a unit of measure of an angle. We're not going to be using degrees in here. We're going to be using radians. And just a quick reminder, 1 radian is 180 over pi degrees. So pi radians is 180 degrees. There's 2 pi radians in a circle. And one neat thing about radians, it's a unit, right? But if there's a unit of length present in the equation or whatever, the radian disappears. So if you have like something in radians times a meter per second, the result is meters per second. It's not radian times meter per second, because the meter just overpowers it. All right. Okay, now we get to the actual quantities. So we have angular position, similar to position, but angular. The symbol for that is theta. It's the just position, but on a circle. And its units is radians, obviously, because that's angle. Angular displacement, again, unit is radians. This is the change in angular position. And unlike regular displacement, this one's not going to, the revolutions add up together. They don't counteract. So if you move 1 full revolution, it's not 0. You would think it is, because displacement would be 0. But the angular displacement allows you to keep on going. So that would be 2 pi as your angular displacement. You go 1 entire circle. Going 2 circles, that's 4 pi, not 0. Be sure to remember that. And yes, the angular displacement, its direction is based on the right hand rule. And I'm just going to write an RHR to show a right hand rule. And for whatever quantity we come across, I'll do RHR for right hand rule. We got angular velocity, which is omega, not a W, omega, it's the Greek letter. And unit is radians per second, because it's just the angular displacement divided by time. And again, there's the average. This is the average one. There's the instantaneous, which is the derivative of angular displacement with respect to time. But I don't need to write both. You should be familiar with that by now because that was just unit 1. And then finally, we got angular acceleration. As you probably expected, it's radians per second squared because it's equal to the change in angular velocity with respect to time, or the derivative if you're talking about the instantaneous one. And yes, it also uses the right-hand rule to get the direction. Okay, and just like we had kinematic equations for regular motion, translational motion, which is what it's called, we also have kinematic equations for rotational motion. And again, it's the same exact equations, but with the angular quantities instead of the rotational ones. I'm going to just show you the 3 big ones. Not all of them because, well, I mean, there's 5, but I'm just going to show you the 3 big ones because they're the ones you're going to use the most. First of all, there's delta theta, which is angular displacement, is equal to the initial angular velocity times the time interval plus 1/2 times the angular acceleration times the time interval squared. That's one of them. You should remember it's similar to the previous one that we learned. Then we got the final angular velocity is equal to the initial one plus angular acceleration times delta t. And then we got final angular velocity squared is equal to initial angular velocity squared plus 2 alpha times delta theta, which all of these should look familiar just using different variables. This is called like Greekifying it because all of these are Greek letters instead of like the regular English counterparts. All right. So if angular velocity and angular acceleration have the same direction, it is speeding up. If they have different directions, it's slowing down, just like in translational mechanics. And you're going to hear me say that a lot. That phrase, just like in translational motion, is probably like one of the main things I'm going to be saying this entire video. All right. Now, how do you convert between linear and angular quantities? So you can actually do delta x is equal to the angular displacement. So displacement is angular displacement times the radius at which it's moving. So if you have like a point on the edge of the circle as it's spinning, that's the radius. If you have a point like halfway there, then you just take the distance from the center to the point you're talking about, and then you find the linear linear displacement of that. Similarly, linear velocity is the angular velocity times radius, and linear acceleration is equal to angular acceleration times radius. Now, there's a little caveat there. It's only one component of the linear acceleration. That's the tangential component. There's also the centripetal component, which you would remember from circular motion. That's equal to v squared over r, as you probably remember. And we have another term for it now as well, omega squared times r, because we have v is equal to omega times r. And so v squared is omega squared times r squared. And now when you're dividing by radius, it's just omega squared r. So that's a nice simple derivation of that. You're probably going to use both of them in this unit, maybe this one more, because it is rotational motion after all. And you can find the total acceleration by, just Pythagorean theorem, because they're opposite, or they're perpendicular to each other. So it's just Pythagorean theorem for that one. All right, so that's basically the kinematics of it. Moving on to kind of dynamics, which is forces. But before we do that, we have to talk about one quantity, and that's the moment of inertia. The moment of inertia is just like mass is in translation motion. It is like the resistance to change in rotational states. So it's like the inertia of rotational motion. And it's given the symbol I. And it has the units kilogram times meters squared. Why, you may ask? Because it is just the sum of all the masses times the radius squared. So for every point, if you have a system of particles, for every particle, you take the mass of it multiplied by the distance from the center of mass squared, and then you add up all of those. So if you have like a big collection of points, you can find the moment of inertia. Let's say the center of mass is there. You just calculate the mass and the radius from the center of mass, and you apply that formula. You're barely ever going to get asked that. You might get asked the moment of inertia of like shapes instead, and I'll get to that in a second. But first, because of this formula, if you have two objects with the same mass, they might not have the same moment of inertia. The moment of inertia is smaller when mass is concentrated near the center. If you have like a donut and a sphere with the same mass, the sphere is going to have a smaller moment of inertia because this mass is farther away from the center of mass this mass is very close, and so this radius term is going to be much smaller for the like the sphere than it is for the donut. Now, onto like moment of inertias of specific shapes. I'm not going to go through them here because there's like maybe 8 to 10 that you probably should memorize. They're not that hard to memorize. You just need to memorize the coefficient in front of them. I'll give you an example. A thin circular ring. So that's kind of like the donut I was talking about. That's just going to be mr squared. If the axis of rotation is there. That's where it's mostly going to be. However, if you have a circular disk, so no hole in the middle, the moment of inertia is going to be 1/2 mr squared. And you can see why with what I told you. There's going to be mass nearer the center, so it's going to be smaller. Now, you may argue, well, there's just more stuff in it, so it's more mass. Well, no, we're assuming the mass is the same. That's why m is there. If the mass is the same, then there's going to be more mass outside than inside, and so the first one's going to be bigger. So those are just two examples, but I would advise you to find a list online and memorize them because it comes in handy. Now, let's say you do forget something. There is a way to get the moment of inertia without like remembering the formulas. I would say it could be harder at times, but sometimes you're actually even forced to use this method. There is a formula for the moment of inertia. This is a formula, but it's for a system of particles. For like a continuous object, a rigid object, you can't use that because then you have to count each particle in the object, which is impossible. But what do you do when you have to add up infinitely many things? That's right, an integral. Welcome back to calculus-based physics. It's the integral of radius squared dm. That looks terrifying at first. I mean, first it looks simple. Then you realize dm, how are you going to get dm? You've been dealing with drs and dx's and stuff like that. How are you going to get dm? Well, there's another form of it, which is just the density times the integral of radius squared dv. Again, because density is just mass over volume, so you can just convert it there. Still looks pretty daunting, but we will do an example of using this formula in one of the problems. So don't worry, I will show you exactly how to do it. It's not as hard as it looks. Just remember that formula. All right, and then related to moment of inertia is something called the parallel axis theorem. Basically saying that the moment of inertia about an axis that's parallel to the original axis is related to the moment of inertia about the original axis. You just have to add a term. So let's say you have like a disk like that, which we know is 1/2 mr squared because of that formula I showed you. And you have, this is the original axis. That's where it's 1/2 mr squared. Let's say you want to do it there instead. You want to rotate it around that. The parallel axis theorem says the moment of inertia around the new point, a new axis, is the moment of inertia around the first axis plus mr squared. This term is always going to be mr squared, which means originally it's 1/2 mr squared, but then you're going to be adding mr squared. In this case, the radius is the radius itself, or the distance you're moving it is the radius itself. And so it's going to still be mr squared. And so I2 is going to be equal to 3/2 mr squared. And if you do find like a list of them online, you can corroborate with that and see that it is indeed 3/2 mr squared. Now, if you were to go like beyond somewhere here, then r wouldn't be the radius of the object. It would just be the distance between the axes. Keep that in mind. R is not always going to be the same thing. All right, so that's the parallel axis theorem. And that's generally considered to be like the first part of rotation. There's obviously like, I think energy is also part of the first chapter of rotation, but we're going to skip that a little later. I prefer going in order. But the second part is going to be where we're introduced to torque and all that lovely stuff. So let's get right onto that. Torque. So torque is a force applied to rotate an object. So let's say you have a circle, for simplicity's sake. It could be a disk, it could be whatever. You apply a force that is perpendicular to the radius from. So that's like the simplest scenario. When you have a force that is perpendicular to the radius, that is going to rotate the object. Think of it like a steering wheel. You grip it and turn it. That's applying a force at some point that is the radius away from the center. So it's denoted with the tau, again, Greekifying all of it. And it is Newton times meter, which is the same thing as energy, but these are not the same like values. Torque and energy are not the same thing. And to prove how, work is also the same unit, right? It's force done over distance that's parallel to it. This is force done to a distance that's perpendicular to it. So what's the formula for it? Well, it is force times radius, or force times distance, if you would like. I'm going to use radius because it is the radius at which you're applying it from. But if you do distance, it'll look more like the work formula. Now, what's the difference between this and the work formula? Well, these both are vectors, obviously. And with vectors, you can do two different types of products. Dot product, which is what we do with work. Force dot a radius, which gives us a scalar quantity. This is called the cross product, which gives us a vector quantity. Basically, it's saying you have these two quantities, you're going to get a third quantity that is perpendicular to both of those. All three of them are vectors. And so if you don't want to do the cross product, it's equal to the force times the distance times sine theta, where theta is the angle between them. So if you didn't apply it perpendicular to the radius, let's say you applied it that way, which looks like it shouldn't rotate it, but there's a component of it that will. This is the radius, and so you do, you can create the component of the radius that is perpendicular to the force, and that's called the lever arm, if you wanted to know. And you multiply that by the force, and now they're perpendicular, so you can use just force times distance. Or if you want, you can use the angle and do F times distance times sine theta. Either one works. So yeah, do a lot of practice on calculating torque. It's not that bad because it's similar to work, but sine instead of cosine. Just think of it that way. You're going to get a vector, though, which is different. But yeah. So what can you do with torque? Well, we had forces. What could we do with forces? Well, there were Newton's laws of motion. There are indeed Newton's laws of rotational motion. There's the three basic laws, but the third law is just if you apply a torque, they're going to apply a torque on you. So let's think of gears. If one gear applies a torque to the other one's going to apply an equal and opposite torque to the first one. All right, that's the third law. The first law is just that if there is no net torque, then the object continues with the same angular velocity in the same direction and all that. Okay, and then the second law is the formula, and so that means that the net torque is equal to, is it mass times the angular acceleration? Well, no, remember, mass in rotational motion is the moment of inertia, and so it's torque, the net torque, is equal to the moment of inertia times the angular acceleration. So this is just force, net force, is equal to mass times acceleration, the one equation we know and love in forces, into Greek, basically, or not Greek because I isn't Greek, but into like rotational motion. Tau is equal to I times alpha. So keep that in mind. That's a pretty important formula to know. That's basically it for torque. It needs a lot of practice, like calculating and stuff like that, especially because you got calculating torque and using Newton's second law. So do a lot of practice. We're going to do a few problems about that, but onwards to work, energy, and power in rotational motion. So work. Work in translational motion is force times distance parallel, like I just said. Work in rotational motion, try to take a guess. You're probably going to get it. It is indeed torque times angular displacement. Again, just very simple converting between these formulas is just whatever you know in translational motion or linear motion, and then just turn the variables into what they are in rotational motion. Very simple. And okay, I should probably write this with the capital W. Oops. Capital W, because I don't want to confuse it with angular velocity, which is the omega. So yeah, work is equal to tau times angular displacement. And again, if torque and angular displacement have the same direction, there it's positive work. Opposite direction is negative work. Perpendicular is zero work. Now, if you have a variable torque, just like with variable forces, work is equal to the integral from the initial angular position to the final one of torque d theta. Again, not bad. Rotational kinetic energy. Similar to kinetic energy, except instead of 1/2 mv squared, it's 1/2 I omega squared. Probably could have guessed that. And then we again have the work energy theorem in rotational motion. Net work is equal to the change in kinetic energy, which is the integral from omega 1 to omega final of I times omega d omega. That seems a bit new, but it's basically saying that I times omega is just another way of writing this, basically, because well, when you integrate it, it just becomes this, and that's because when you integrate omega, you get angular acceleration, and I times angular acceleration is torque, and then this d theta has to do with the displacement. And so you're probably not going to use this that much, but it's mainly this. The net work is equal to the change in kinetic energy. We also got gravitational potential energy. That's basically the same thing. And then we got power. Power is the change in work over the change in time. And the instantaneous power is torque times omega, because the instantaneous power in linear motion was force times velocity. It's the same thing here. All right. Now you can use this to solve motion problems. A lot of motion problems, once you get to this part of the unit, can be much are simplified with the use of energy, with like conservation of energy and all that. So one example is rolling down an incline. And I think you did do a lab where you roll different objects down the incline. And the conclusion of that is object with smaller moment of inertia reaches the bottom first. So you can actually like solve for variables and stuff like that. If you're given like the distance you roll and the moment of inertia, or like the mass and radius and things like that, and the angle of the incline and all that, you can actually solve for like the velocity and the time it takes and things like that. But we're not going to be doing that here, because you're probably never going to use those formulas ever again. Our final topic for the day is angular momentum, just like momentum, but angular. So it's the momentum due to rotational motion, denoted with an L. Its unit is kilogram times meter squared per second. All right. And again, it uses the right-hand rule. Same with torque. I forgot to mention this, but torque is also dependent on the right-hand rule. The direction is the right-hand rule, as is angular momentum. What is the formula for angular momentum? Well, the angular momentum is equal to the radius times the mass times velocity. So the mass times velocity we know is momentum. When you multiply that by the radius, just like with most other linear quantities, you're going to get the angular version of it. Or actually, it's the other way around here. Usually, you get something like v is equal to omega times r. So the angular times the radius is equal to the linear. In this case, the linear times the radius is equal to the angular. So be careful of that. But yeah, it's a similar trend. Not the same, but similar. This is also equal to, again, this is the cross product, because because the result is a vector. And so it's going to be mvr times sine theta. Another formula for the angular momentum is the I times omega. So this is what I was kind of talking about a bit earlier. I jumped ahead a bit. This is the angular momentum. So the integral of angular momentum is equal to the work done. It's similar to the integral of momentum being the work. Now, I don't think we ever talked about that, but if you consider momentum to be force is equal to dp over dt. And so if you do something similar here, you're going to get the exact same thing. So probably not going to use that formula, but it's there if you want it. And like I just said, force is dp over dt, the derivative of momentum with respect to time. Torque is the derivative of angular momentum with respect to time as well. Right, and then there's conservation of angular momentum. So angular momentum, it remains constant. Total angular momentum remains constant if there's no net external torque. And yeah, that's basically it for rotation. So yeah, that's it for our content review, and moving on to the practice problems. This one is pretty long because, rotation is a long unit. It's basically like 2 chapters. And so we had to squeeze all of that in there. Moving on to the practice problem. So starting with this one. At t equals 0, grinding wheel has an angular velocity of 24 radians per second. It has an angular acceleration constant of 30 radians per second squared until a circuit breaker trips at 2 seconds. From then on, it turns through 432 radians as it goes to a stop. Through what total angle did the wheel turn between 0 and the time it was stopped? Okay. So we can use one of our kinematic equations here. The angular displacement is equal to the initial angular velocity times the time plus 1/2 angular acceleration times the time squared. So we know this was 24 radians per second. This was 2 seconds plus 1/2 times 30 times 2 squared. So again, I'm not including decimals or units or anything because it's just a simple one. But you would calculate this, and you're going to get a total of 48 radians. Or sorry, 48 plus 60 is 108 radians. Is going to be from 0 to 2 seconds, and then another 432 radians. So 108 plus 432 is 540 radians. So that's your answer to part A, which is what was the total angle. B, at what time did it stop? All right, so we could do another kinematic equation here. So this one I actually didn't go over because I didn't think it would pop up that much, but it's the equation that angular displacement is equal to initial angular velocity plus final over 2 times delta t. And this is only if there's constant angular acceleration, which there is. Again, you should probably know this from linear motion, or like unit 1, so I didn't really cover it, but yeah. There's actually other ways you can do it. You can use other kinematic equations to solve for the angular acceleration, but that's what part C is asking for. So better to do this first and then part C. Yeah, anyway, so we know this is 432 because it's only after the circuit breaker trips. You know the initial is... do we know the initial? Oh, we don't yet, but we can solve for it. We know that the final angular velocity until the circuit breaker trip. So that's basically the initial that we're looking for now is equal to the initial plus the angular acceleration times delta t. The initial was 24, angular acceleration was 30 times t is 2. So it's 24 plus 60, which is 84 radians per second. So this becomes 84. The final is 0 because it's slowed down to a stop. And we find out what delta t is. 84 plus 0 over 2 is 42. And so 432 divided by that is equal to 10.3. So 10.3 seconds is our answer to part B. And then for part C, it's asking for the angular acceleration. Again, we could have found that earlier actually, but we can just do final angular velocity is equal to initial plus angular acceleration times delta t, same equation as before. This time the final is 0 because it stops. This is 84 because that's this. And then 10.3 seconds is what we know. So we just have to solve for angular acceleration. So move the 84 to that side. That becomes negative 84 is equal to 10.3 times alpha. And just divide by 10.3 to get alpha. And you're going to get negative 8.16 radians per second squared. And I just realized something here. It says, at what time did it stop? 10.3 seconds since the circuit breaker trip, but I actually forgot to add the 2 seconds from the start. So it's 12.3 seconds, because first it went 2 seconds, then 10.3 seconds. So it's a total of 12.3 seconds. So yeah. All right, that was the first problem. Moving on to number 2 here. And again, as always, if you want to try these problems by yourself before I give you the answer, feel free to do that. Just pause the video, do it, and I'll show you how to do it. All right, for this one, we got the diameter, we got initial angular velocity and angular acceleration, just like before. Calculate the angular velocity after 0.2 seconds. So they did give us the velocities in revolutions per second. So at some point we want to convert it into radians per second. And the way to do that is, well, there's 2 radians in 1 revolution. So we just multiply by 2 pi and change the units. We don't need to do that yet because it's still asking us for the angular velocity, which we can still give in revolutions per second. In fact, they're probably expecting that because they gave us the initial one in revolutions per second. But part B is how many revolutions. Again, we don't need to convert. It's better if we don't convert until then. C is the tangential speed. That's when we need to convert. So for now, let's just keep it in revolutions per second. This is the same exact equation. W final is equal to initial plus alpha times delta t. Omega final is what we're trying to find. This is 0.25 plus alpha is 0.9 times t is what was it, 0.2. And so 0.9 times 0.2 gives us 0.18. And then you add that to 0.25, we're going to get an final angular velocity of 0.43 revolutions per second. For part B, it's asking how many revolutions has it spun in this time. So that's going to be is equal to the average angular velocity times delta t. Again, the equation that I didn't go over, but it's always there for you. So we know it starts off with 0.25, and then that's 0.43. Delta t is 0.2, and so 0.25 plus 0.43 is going to be 0.68. Divide by 2 is 0.34, multiply that by 0.2. You're going to get a delta theta angular displacement of 0.068 revolutions, because we're still in those units. All right. Part C. Now we convert to radians. So we just do 0.43, because it's asking us for the tangential speed at 0.2 seconds, so that's the final one. 0.43 times 2 pi. Now, we could save us some calculations and just calculate this is equal to omega times r. So we do the 0.43 times 2 pi, and then multiply that by another value, radius, which is 0.75 over 2, which is 0.75 over 2, 0.375, because 0.75 was the diameter. And you multiply all that, you're going to get 1.01 meters per second. Because the meters chases away the radians, our units is going to be meters per second. All right, and then for part D, what is the magnitude of the resultant accelerations? This time we have to do both centripetal and tangential. Tangential is just going to be alpha times r. We know alpha is, what was it, 0.9. Radius is 0.375, 0.75 over 2. And we have to multiply by 2 pi, because it is currently in revolutions per second squared. We want it in radians per second squared. All right. So that's the tangential one. I'm not calculating them yet, so that we can save calculations and just do it in one all go. And then for the radial one, it's omega squared r. We can use that formula. Oops, not omega r squared. Omega squared r. Omega we know is 0.43 because it's at 0.2 seconds. Oops. 0.43 squared times radius of 0.75 over 2. Multiply that out. 0.43 is multiplied by 2 pi. We get the one. We're given this. So instead of omega squared r, we could also do v squared over r, and just do 1.01 squared over radius of 0.375, and we get our centripetal acceleration. Then acceleration is just square root of ac squared plus at squared, and if you were to solve for all that, you got this as ac, this is at, and then you square root that, you're going to get 3.46 meters per second squared, which is our answer. All right, moving on to the next problem. Number 3 here. So this is the one I was telling you about. You calculate the formula of moment of inertia for a uniform rod with mass m and length l about an axis of at one end perpendicular to the rod. So how would you do this? Let's say you don't know the formula. You could have memorized it. This could be one of the ones you memorized. Maybe not at the end. Sometimes you would memorize through axis that is right at the center, but you can use the parallel axis theorem to get it at the end. But let's say you don't know that, because it's asking us to use the integral equation. How would you solve it? Well, when you see integrals, you think graphs, right? Calculus. And so you can put this rod on the graph, on the x-axis, and you get something like this. Now, the thickness doesn't matter. Like, this thickness doesn't matter. What matters is this length L and the mass m. Those are the two things that it tells us. And here the axis is like right here. It's at one end. So how would we solve for this? Well, the formula is I is equal to integral of r squared dm. And we want to convert dm into dr because, or x in this case, because it's the x-axis and y-axis. We want both of them in x because that way we can actually solve the integral. And so you want to take a slice of this, because that's what integrals are. You just accumulate many slices, and that is dx. Now, if you find the mass of that slice, that's dm. What is the mass of that slice? Well, it has to do with dx, because dx is the like the coordinate or whatever of that slice, the thickness of the slice. If you're given the thickness of something, let's say you actually have the rod in front of you and you take off a piece of it, a big chunk. How would you find the mass of that? Well, you can use the density, and since the density is constant throughout, you can do the density times how much ever you got, and that gives you the mass. We're basically going to do the same thing here. We're not given the actual density, and we don't want the actual density, because all we care about is this one-dimensional density. All we care about is this thickness, and so we want the mass over the length. That gives us like the mass per unit length, and once we multiply that by the length we have, we're going to get the mass of the slice that we have. So dm is equal to m over l times dx. Okay, with that in mind, we can plug this back into the integral. R is x in this case, because it actually might be easier if I turn the dotted line, if I turn the dotted line here to this axis. I didn't want to interfere with the axis, but it's actually better. Now, if we consider r to be x, from 0 to this point L, that's basically the moment of inertia. You're taking all the slices from 0 to L. If you wanted it from the middle, you would go from negative L over 2 to L over 2, because you're treating this as the axis now. But we're going from 0 to L because it's from at one end. So it's x squared times dm. dm is m over L times dx. And so m and L don't have anything to do with x, so they're constants. We can move them out. It's m over L times the integral from 0 to L of x squared dx. We know how to do this. This is just calculus. Integral of x squared dx is just going to be 1/3 x cubed plus c, but since it's definite, it's from L to 0. And again, m over L. So it's m over L times 1/3 L cubed minus 0, which is just 1/3 L cubed. And so this becomes 1/3 m L squared, because the L cubed and the L cancel off, leaving L squared. And so your answer would be I is equal to 1/3 ml squared, which actually is the result. That is what you get if you search it up. And so this method actually works. It's not as scary as it looks, because you can just convert the dm into dx. Now, if you were given something like a sphere, what might be easier is using the other form of the equation, which is rho times integral of r squared dv, and calculate the v in terms of the radius, which is very easy. You should know how to find the volume of a sphere. And then, just turn that into dr. For example, v is equal to 4/3 pi r cubed. And so dv, it's like calculus. You take the derivative of both sides, you bring down the 3, so that's 4 pi r squared times dr. So dr is equal, dv is equal to this. You just plug that instead of dv, and you get something very similar to what we did for this one. All right. Number 4. I know it's very slow, but this is a long unit, and a lot of work needs to be shown. So let's do it. We got there's this solid uniform cylinder, and there's a rope that's tied around it, and there's a bucket of water here. We know the radius, or the diameter of it, is 0.3, so radius is 0.15 meters. Mass is 12 kilograms. This is of the cylinder. Frictionless axle bucket is released from rest at the top of the well and falls 10 meters into the water. What is the tension in the rope while the bucket's falling? It might seem obvious, like, why do we need rotation for this? It's just gravity and tension. But remember, it's accelerating downwards. We don't know what that acceleration is, but we can use rotation to figure it out. This seems like a forces problem, but actually, you need rotation to solve this. And it's one of my favorite types of problems, because it's like combining rotation and linear motion pretty nicely. So let's draw a free body diagram for the bucket. We got gravity down here, which is mg. We got tension up here, which is less than gravity. What does that mean? Well, we can write a force equation for it. It just means that Fg, well, this is Fd. Fg minus Ft is equal to mass times acceleration. So mg minus ft is equal to mass times acceleration. All right. That's basically all we could do for the bucket. That's all we would have been able to do without rotation. With rotation, we can do something else. And that, namely, is Newton's second law for rotational motion. We know that the net torque is equal to moment of inertia times angular acceleration. And so what is the net torque? Well, there's a tension force going downwards. It's perpendicular to the radius, and so it's the force of tension times the radius. And that's equal to the moment of inertia. You would probably need to memorize it for a solid cylinder. You could derive it, but I wouldn't suggest that. It would take too long to derive it. But if you memorize it, it's going to be 1/2 mr squared. This is the same thing as a disk, basically. Like a solid cylinder is the same thing as a disk. And then times alpha. And we know alpha is equal to the acceleration divided by the radius. And again, for consistency's sake, this is going to be big R because I used that later on without realizing it. So alpha is acceleration over radius. Because we know linear acceleration is, or tangential at least, is equal to alpha times radius. And so you just go the other way around. And what that tells us is we can cancel off with one of the radii. So it becomes m times r times a. And the r's cancel nicely. We're left with ft is equal to 1/2 ma. We can plug that into here, where this small m is the mass of the bucket, this big M is the mass of the cylinder. And we're going to get mg is minus 1/2 ma is equal to ma. What can we do from there? Oh, it did give us the mass of the bucket, I forgot, 15 kilograms. All right. Wow, the bucket's heavier than the cylinder. Okay, anyway, we want to solve for acceleration and then use that to solve for tension. What we're going to get is 1/2 ma plus ma is equal to mg. And so a times 1/2 m plus m is equal to mg, or a is equal to mg over 1/2 m plus m. All right, now we know all of this. Lowercase m is 15 kilograms, g is 9.8, uppercase m is 12 kilograms, lowercase m is 15 kilograms. And so plugging all that in, we're going to get an acceleration of 7 meters per second squared, 7.00. And so the tension would be 1/2 times big M, which is 12 times 7. So 12 times 7 is 84, 1/2 of that is 42. So tension force is equal to 42 newtons. And keep in mind that's all for part A. But parts B, C, and D are much easier than that. Unfortunately, I'm going to have to erase this to fit parts B, C, and D. But remember, tension force is 42 newtons, acceleration, or linear acceleration, is 7 meters per second. For part B, with what speed does the bucket strike the water? Okay, this is just kinematics. Linear kinematics, mind you. V final squared is equal to V initial squared plus 2a delta x. Or delta y in this case because it's going vertically, but it doesn't really matter. We know V initial is 0 because it starts at rest. Acceleration is 7. We just calculated that. And this is 10. So 0 plus 2 times 7 times 10. 2 times 7 times 10 is 140. So square root of 140 gives us a V final of 11.8 meters per second. All right, like I said, the next ones aren't bad at all. For part C, it's what is the time of the fall? Okay, again, kinematics. This time we can do multiple different formulas. I'm going to do delta y is equal to VIY, or VI delta t, plus 1/2 a delta t squared. And we know a is 7. We know this is 0, so this entire term is 0. And we know this is 10. So this just becomes 10 is equal to 1/2 times 7 times delta t squared. So that's basically 10 divided by 3.5. And then the square root of that, you're going to get delta t is equal to 1.69 seconds. And then part D, while the bucket's falling, what is the force exerted on the cylinder by the axle? Okay, this one's a bit trickier. So if you have the cylinder and you have the axle, let's draw a free body diagram for the cylinder. We got the force of gravity because it does have some mass. We got the force of tension pulling it down because of that string. But we do have the normal force pushing it up because that's what the axle is exerting on the cylinder. it's keeping it up. If it wasn't there, the cylinder would also fall down. And so the equation for this is Fn minus Ft minus mg is equal to 0. This is actually the bigger m, because it's a cylinder. We basically know all of this. Ft is 42 newtons, m is 12 kilograms, and g is 9.8. And so 12 times 9.8, and then also the 42 added together make 160, and so the normal force would be 160 newtons. Again, just math there. All right, and that's it for this first four. And then we have another four down there, which is fun. Okay. For this one, we got a merry-go-round, radius 2.4 meters, moment of inertia of 2100, vertical axle to the center, turns with negligible friction. Child applies 18 Newton force tangentially for 15 seconds. If the merry-go-round is initially at rest, what is the angular speed after this 15-second interval? All right, so that's just kinematics, right? Well, there's also torque involved, because the child applies 18 newtons force tangentially, so there's no theta we have to worry about. It's just the force applied times the radius, which is 18 newtons times 2.4 meters, because that's the radius. And then we know that's equal to the moment of inertia times the angular acceleration, because that's just torque. And we know a Newton's second law. Moment of inertia was 2100, so angular acceleration is just 18 times 2.4 divided by 2100, which is 0.02057 radians per second squared. It's not asking for the angular acceleration, it's asking for the angular speed. Now we just do the kinematic equation. So that is basically omega final is equal to omega initial plus plus a delta t, or alpha delta t. Sorry, this, it starts at rest. It says that, right? Yeah, if the merry-go is initially at rest. Yeah, so this is 0. Alpha is this 0.2057. 0.02057, and this is 15 seconds. So you just multiply those two, that's 0, so it doesn't matter. And we find a final angular velocity, angular velocity of 0.309 radians per second. And so that's going to be our answer for part A. For part B, how much work did the child do? Well, work is equal to torque times angular displacement. Now, first of all, torque is constant because it's a constant angular acceleration, but we don't know the angular displacement. We can find that using kinematic equations. Angular displacement is initial angular velocity times time plus 1/2 alpha delta t squared. This is 0 because angular, it starts at rest. Alpha is 0.02057. Time is, what is time? 15 seconds. And so you do 1/2 times 0.02057 times 15 squared, and you're going to get a delta theta of 2.314 radians. All right. Now we multiply that by the torque. Torque we didn't actually calculate, but it's 18 newtons times 2.4 meters, which is 43.2 Newton meters. And we multiply that with the angular displacement we got, and we're going to get a work done of 100 joules. All right. And then finally, part C, what is the average power? That's simple. That's just work over time. 100 joules power is equal to 100 joules over, 15 seconds. And that's just 6.67 watts. And that's your answer. Not bad there, just work energy power. Our next one is a very fun problem where there are no numbers, which I honestly like. But it's just, you have to find the fraction of total energy that is rotational for the following objects rolling without slipping on a horizontal surface. And you got 4 different objects, and it doesn't give you much information at all. You just need to know the moment of inertia formulas. But before we do any of that, I want to take you on a journey to calculate what the fraction of total kinetic energy is rotational for any object with a given moment of inertia. So let's do that. when an object's rolling, it has two different forms of energy, linear and rotational. The linear energy is 1/2 mv squared, and the rotational energy is 1/2 I omega squared. All right, good. We know omega is equal to v over r because v is equal to r times omega, and so 1/2 I times v over r squared. So it becomes 1/2 IV squared over r squared. Alternatively, you could turn this into v is equal to omega r, and so this becomes 1/2 m omega squared r squared. Either way works. I'm actually going to do the second way because I don't like fractions very much. And so this is going to stay 1/2 I omega squared. Now, the fraction that is rotational is going to be 1/2 I omega squared over 1/2 I omega squared plus 1/2 m omega squared r squared. Halves cancel off nicely, and the omega squares also cancel off. It's just I over I plus mr squared, basically. Now, you could simplify it a bit by dividing by I, the numerator and denominator by I. We're left with 1 over 1 plus mr squared over I. And that's going to be your formula. Just a simple derivation with the two definitions of kinetic energy, and that works for any object. You just need to know the moment of inertia formula for that object. So, getting rid of this derivation, now that makes the rest of the problem simpler. A is a uniform solid cylinder. We actually encountered this before. It's going to be 1/2 mr squared. And if you plug that in here, you're going to get 1 over 1 plus 1/2 in the denominator. So it's mr squared over 1/2 mr squared. This cancels off. We're left with 1 over 1 plus 1 over 1/2, which is just 1 over 1 plus 2, or 1/3. And so that's going to be your answer for the first part. Second one is a uniform sphere. We didn't encounter that, I think, but that's 2/5 mr squared. So that becomes 1 over 1 plus 1 over 2/5 if you just simplify the mr squared like before. So that's 1 over 1 plus 5 over 2, which is 1 over 7 over 2, which is 2/7. And so that's going to be the answer for part B. C is thin-walled holosphere. Again, don't know this, but it's 2/3 mr squared. Memorize it. Very helpful. That becomes 1 over 1 plus 1 over 2/3, which is 1 over 1 plus 3 over 2, which is 1 over 5 over 2, which is 2/5. And then finally, part D is a hollow cylinder with outer radius r and inner radius r over 2. This you might not even memorize, but you could derive it, or you might end up memorizing it. It's going to be 5/8 mr squared. So it's 1 over 1 plus 1 over 5/8. And that's equal to 1 over 1 plus 8 over 5, which is 1 over 13 over 5. So it becomes 5 over 13. So those are going to be your answers for this question. All right, just 2 questions left. Not bad, almost done with the video. This one is just like using energy to solve rotational problem. Kind of like what I was talking about in the content review. Energy makes these problems a lot easier. Okay, we got a diameter of 22.6 centimeters. So our radius is going to be 11.3 centimeters, or 0.113 meters. Mass is 426 grams, or 0.426 kilograms, because we want to convert to base units. Okay, it's a thin-walled hollow sphere. Now, if you actually remember from the previous problem, we know a thin-walled hollow sphere is 2/3 mr squared. Good to know. And at what rate was it rotating at the base of the hill? Now, it doesn't seem like energy would be very useful here, but it actually would be, because the rate it was rotating is omega. It's the angular velocity. And omega is part of kinetic energy, rotational kinetic energy. And we know that it went up to 5 meters above the base of the hill. And so we have an initial kinetic energy and a final potential energy. Let's just make sure those are the only energies. We have K1 plus U1 equals K2 plus U2. Oops. K2 plus U2. Well, at the start, it's at the bottom of the hill. There's no potential energy. At the end, it stops moving because it reached its maximum height. So there's 0 kinetic energy. And just K1 equals U2. K1 is Well, technically, we need both the linear and rotational velocity because it's rolling without slipping. 1/2 mv squared plus 1/2 I omega squared, and that's equal to mgh, just simple potential, gravitational potential energy. Now we know I is 2/3 mr squared, so it becomes 1/2 times 2/3 mr squared times omega squared, and so that's 1/3 m omega squared r squared. Well, what's omega r? Well, that's just v equals omega r, and so omega squared r squared is 1/3 mv squared. Nice. So it becomes 1/2 mv squared plus 1/3 mv squared. Again, I'm switching between capital M, lowercase m here. It doesn't really matter for this problem because there's only one object. So yeah, it's probably best practices to maintain consistency in your work. But this is just quick calculations. So this is equal to mgh. The mass cancel off, so it doesn't even matter anyway. But 1/2 plus 1/3 is 5/6, and so 5/6 v squared is equal to gh. V is equal to square root of 6gh over 5 if you multiply it by 6 and divide by 5 square root. You know g is 9.8, h is 5 meters, so you get a v of 7.67 meters per second. And so omega would be that divided by the radius, which is 0.113 meters, and so omega is 67.9 radians per second. That was just for part A. Part B is rotational kinetic energy. That's easy. That's actually just this formula because it was 1/2 I omega squared, but we simplified it down to this based on what we knew of the rotational inertia the moment of inertia and things like that. So it's 1/3 times the mass, which is 0.426, and then velocity, linear velocity, is 7.67 squared. You multiply all that out, that becomes K is equal to 8.35 joules. Is your answer for part B. Great. And then last question. This is actually one of my favorite questions because it literally doesn't give you much information at all. And it seems like it's not possible, but it very much is so. All right. We got Earth, and we got an asteroid. So it's saying there's the planet. Earth's mass is m, and it doesn't tell us this, but let's just assume Earth's radius is r. If it doesn't tell us this, it's not going to matter. But for like moment of inertia calculations and things like that, we might want to use that, and so it'll probably get canceled out in the end anyway. What is the mass of this asteroid? It's lowercase m, and we want to find out what lowercase m is in terms of uppercase m. And it says, assume that the asteroid is very small compared to the Earth, and the Earth is uniform throughout. Okay, so if the asteroid is very small, its radius is 0. It's not really 0, but it's negligible, and so we don't really care about it that much. And you might be thinking, okay, how are we going to solve this problem? Let me introduce you to our friend angular momentum and the conservation of angular momentum specifically. So what is the original angular momentum of the Earth? Well, it's going to be the moment of inertia of the Earth times omega. And I'm going to call that omega initial because that's before it gets hit. Moment of inertia of the Earth. So it is considered like a uniform sphere because it says assume that the Earth is uniform throughout. And I know it's not a perfect sphere, but we're assuming it is. It's going to be 2/5 mr squared is the formula, and we multiply that by omega initial. What about the angular momentum of the asteroid? Well, it would be negligible in this case because it's not part of the system yet, and also because it has very small radius and things like that. But once it hits it, then it is like it's part of the Earth now. So it has a moment of inertia as well. So when you combine two objects, you add up their moment of inertias. So now you got an Earth with a little blob sticking out from one side of it. So the Earth itself is 2/5 mr squared, but this little blob has a mass of m, and it is a distance r from the center of the Earth. Same r in this case, capital R. So it's actually just going to be m, lowercase m, r squared. That is going to be the moment of inertia of the asteroid with respect to the Earth's center, like the axis of rotation of the Earth. which is pretty counterintuitive, but it's a mass m. Think of it like the other formula for a moment of inertia, which is just like a collection of particles. Think of this as a particle because its radius is negligible. So it's mr squared. And that times the final angular velocity. So we can distribute it out. We get 2/5 mr squared omega initial is equal to 2/5 mr squared omega final plus mr squared omega final. Subtract from both sides, we get 2/5 mr squared, and we can factor that out. It's omega initial minus omega final is equal to mr squared omega final. Like I said, radius cancels out nicely, and we divide by omega final. We're going to get 2/5 m times omega initial minus omega final over omega final is equal to mass. Now, if we just solve for what this is, we can get lowercase m in terms of uppercase m, which is what we want. How do we solve for that? Well, that's where the day becomes 25% longer. So it might not be obvious at first, but the length of the day is going to be 2 pi over the angular velocity. Why, you may ask? Well, the angular velocity is how fast it's spinning, and if it spins 2 pi radians, that's one entire revolution. So how long it takes to spin 2 pi radians is going to be 2 pi over omega. Think of it like in circular motion when t is equal to 1 over f, which is 2 pi over the angular frequency. I believe you covered that. It's the same thing here. The amount of time it takes to travel 2 pi radians is 2 pi over the angular speed. So with that in mind, if the T2 is equal to 1.25 times T1 because it's 25% more. That means 2 pi over omega 1, omega 2 is equal to 2 pi over omega 1 times that 1.25. And I realize it's omega final and omega initial, but it doesn't really matter. It's the same thing. The 2 pi's cancel, and we're left with omega 1 is equal to, or omega initial, it doesn't matter, 1.25 times omega final. And so plugging it back in here, 1.25 times omega final is 1.25 omega final minus omega final over omega final, which is just 0.25 omega final over omega final, cancels out. We're left with 0.25. So our final equation is mass equal to 2/5 times the uppercase mass times 0.25 or 1/4. And so lowercase m is going to be equal to 2/5 times 0.25, which is just 0.1 or 1/10. Times the uppercase mass. So our answer is what the mass of the asteroid is for the day to become 25% longer is a mass of 0.1 times Earth's mass. And that's very, very big. Like 10% of Earth's mass, that's a huge asteroid. Which is why when asteroids hit Earth, we don't really see the day speeding up that fast. 25% is a long time. And 10% of Earth's mass is a very large mass. And so the answer, I guess, makes sense because, very large mass, very large change in day. If it was like 0.0000001 mass, then that could be closer to like what we actually see, which would be like a very like 0.0000025% change in the day, which is barely noticeable at all. Anyway, that was just one of my favorite questions because it looks very difficult to solve, and it kind of is pretty difficult to solve compared to the others. But if you think about it a little, you'll get it. And that marks the end of this video, and not just this video, AP Physics C Mechanics. So good luck on your rotation test, and I'll see you for electricity and magnetism with our first unit, electrostatics. So see you then, and good luck.